All right, morning. This is Calculus 1. 1.4 limits, continuity, trigonometric, exponential, and logarithmic functions. Woo, yeah. All right. Okay. Squeeze theorem. Find a limit. Find limits involving trigonometric function. Determine whether the trigonometric functions are continuous. Now, there's a couple things I'm going to have you guys highlight. Okay. So, on this one right here, this is what squeeze theorem is. Squeeze theorem is when I have the limit, the lower part of my function, and the upper part of my function are both going to the same thing, right? Therefore, that would be the limit of this function. It would be the limit because we're looking for the left hand, the right hand, and we're squeezing it in there. So you guys are going to see some interesting problems. Now, because squeeze theorem, it's not a regular line. It's like a wiggly line. It's a squiggly line. It does a little up and down thingy. Okay? So, yeah, you'll see it. Anyway, all right, so if this side is equal to this side, there and there, that's equal to the limit. So therefore, the g of x, which is between both of those, is going to be that limit. All right, basic trigonometric limits. So the limit as x approaches 0 of sine gives me 0 because it is right here. Okay, this is actually a sine wave. Now, next one, cosine wave. The limit as x approaches 0 of cosine is equal to 1 because at 0, x is 1. Just by basic graph. Ah, that's cheating. No. Okay, so now this one's going to be something interesting. So what we're looking at this one here is we know a couple things here. So for this, I know that the sine, so as theta, for this one right here, as theta goes to 0, that's basically the same thing as saying x goes to 0. Okay, this time theta is my variable, because this is a trig function. So as theta goes to 0 for this, we're going to have a couple things here. So I'm going to start off with multiplying. Okay, I'm going to multiply here. Okay, so we're going to take this and it's going to be sine of 3 theta over theta. So multiply 3 over 3. By multiplying top and bottom of 3 over 3, that's going to give me the same thing here and here. Right? Because I want to have the same thing there and there. So that brings up an identity. It brings up an identity that we're going to have. So we're going to, the identity is actually on the next, forgot to clear my things. Did I skip the identity? I did. The identity is not there. Okay, anyway. So the identity that we have, okay, I guess I forgot it in my notes somewhere. So my identity is going to be the limit as x approaches 0 of sine x over x equals, now, I want you guys to take a look at it. Put it in your graph real quick. Because it's going to be identity. If it's an identity, that means it's always going to be something. So put that in your graph. Does it look interesting? So, do you have something that's like squiggling up and down? Wiggle, wiggle, wiggle. Okay, does everyone have it? Okay, what does it look like it's going to? What does it look like? Say it. It looks like it's going to 1, isn't it? So I am going to, right here, show you. So we have sine. So when you're doing this, make sure your calculator's in radian, because that's going to be really important. Because if it's in degrees, that means it's going to mess you up. Sine x over x, enter. Hey, look, right there. This is an identity. It's going to go to 1. Okay? So there's my wiggly line. So my identity, when this is the same, is going to be 1. Now, can I apply that identity to this problem that I have right now? Yes. So x over x, that means that these two things have to be the same. So if they're the same, the identity applies. So on this case right here, this is now going to be 3 sine of 3 theta over 3 theta. That's why I multiplied by 3 over 3 here, right? Yes. Yeah. Okay, multiplied by 3 over 3 here. So now I have 3 theta and 3 theta here, right? Mm-hmm. So now this whole piece right here turns into 1. Now, if this whole thing is going to be 1, I still have this out here. So that's going to give me 3. Because it's 3 times 1. This piece is 1. Does that make sense? Or no sense at all? More sense? Muy or nonsense? Alright, so now that we have the identity and we have that, so, we gotta do some interesting stuff for this one right here. So now the limit as theta approaches 0, let's see what this one would be. If I were to graph this, multiply by what? Now, why could I not just plug in 0 for this problem right here? You can't have 0 on the bottom, right? You can't have 0 on the bottom. So now, can I plug in 0 down here for B? No, because 2 times 0 is 0. And what's the sign at 0? 0. So I still cannot have 0 in the bottom here, right? So now I have to do some voodoo magic. Okay, so we're going to do some voodoo. We don't know the voodoo that you do. Okay, anyway. All right, so let's go through and see what this would be. Let's try and graph this bad boy. Start by graphing and see where we can apply. Huh? 5 over 2? Okay, so now if we notice, do I have a theta though? I don't. On this one, I don't have that theta, right? So my identity says sine x over x, right? Am I missing the same thing on the bottom?
Why? Because it's a common. Oh, because like it's another side on the bottom.
Yeah, I need to have another variable too. I can't just 5 over 2 or 2 over 5, right? So what would I multiply that by? Okay, we got to do some trickiness here. Okay, so now if we're doing some trickiness here, I know a couple things. So would I be able to take out the top part here? I know I could take care of the top part, right? Say yes.
Sure.
Okay, because I know sine x over x. So what would I what would I multiply just to take care of the top?
Sine 5.
No, not the sine. Just
5 theta?
5 theta. So it'd be 5 theta over, and that would be sine of 5 theta over sine of 2 theta. So that takes care of part of it, right? Because the sine 5 theta over 5 theta is going to turn into what? 1. That's going to turn into 1. So now I have 5 theta over sine of 2 theta. I still can't plug in theta, can I? I can't plug in my 0, can I? So what could I do? Could I do something else creative?
Where's the theta on here?
Theta? Oh, you don't use theta. Use
Just x?
yeah, just x.
Isn't this basically the same as that? It must be like they're flipped.
Okay, very good. So if I were to take this right here, right? I'm going to take this right here. Now, isn't this right here over 1? That's over 1, isn't it? Okay, all parts I could say is going to be over 1. So I could say that this is going to be over 1. Just the numerator is over 1, or the denominator is over 1. So I could turn it into a fraction over fraction, right? Okay, so I could turn it into 5 theta over 1 over sine 2 theta over 1, right? Yes? Okay, so I'm going to multiply just the bottom right here by what? Say it. 2 theta over 2 theta, right? Now, doesn't that come out to be 1? It's the same thing top and bottom, so I'm not changing the value. I'm just changing what it looks like. Now, once I have that, what am I going to do? I know my sine 2 theta over 2 theta is going to do what? That's going to cancel that out, right? So this and this turn into 1. So now I'm going to be left with 5 theta over 2 theta. Right? Because this is 2 theta over 1, so it could be just back as without being over a fraction, right? Without being over 1. So now, what could I do with those thetas? Cancel. Let's cancel those thetas. So I'm left with 5 over 2. Now, that's doing all the math, but I still haven't actually done this part right here, the limit part. Okay, so now, is there a variable left there? Say no. No. So we did all this right here just to finally do this last thing, because I'm removing parts of it. I'm factoring out parts of this. I'm separating up my function so I could take out pieces. So now it's the limit as theta approaches 0 of 5 over 2. Is there a variable in there? There's no variable. So the limit as theta approaches 0 is going to give you what? 5 over 2. Because this 5 over 2 has no variable to plug in as 0, right? If there was a variable here, I would plug in 0 and get what? 0, right? But since there is no variables here, I get the number 5 over 2. So, we did a bunch of voodoo over here. You guys okay with that, or there will be tears later?
There'll be tears, but I get it.
Okay.
It probably won't be good.
Okay, so now it will be reinforced and talked about more and more of these identities. Now, this next identity, I actually did make sure it's in there. So, another identity.
Going at me.
Hey, shh.
It's fine.
Okay, I have an identity here. So this identity is going to be the limit as theta approaches 0 of cosine theta minus 1 over theta is going to give me 0. Okay, I will use that identity often. So those two identities that I talked to you about, so the one with sine and the one with cosine, we're going to use often. Okay? All right, so, and radians, always radians. Showing f of x equals sine x is continuous at 0. Sine function, sine x is continuous on all its domain, all real numbers. Is there any holes in the function sine x? Say no. I even told you the answer. Come on, you guys. All right, so it's continuous. There is no holes. That means there's no jumps in the track, right? There's no jumps in the track. It goes on forever. Sine is a wave, right? Same thing goes for cosine. Cosine is also a wave with a phase shift that's pi halves. But it's the same thing. Is there any jumps in the track? Say no.
No.
There we go. All right. Okay. Now, right here, tangent. So tangent, cosecant, and secant, and cotangent, they're all going to have in their domain, they're going to have places in which that there are jumps in the track. These are going to be asymptotes for these functions. So they are not continuous. So you have to look closely at its domain. So the domain of tangent is from negative pi over 2 to negative pi halves to positive pi halves. So from those two places, if you were to graph it from there to there, it is continuous. But it is excluding. So it is parentheses around that. So it is continuous on a open interval. That means it's not including the endpoints. Does that make sense? Because every place, every multiple of pi over 2, I'm going to have another asymptote. So you guys know a tangent graph. Tangent graph goes up. Okay, looks kind of like an x cubed, but not as sharp. Okay. All right. Cosecant and secant are both u's. They're u's going up and down. Okay, together, but they skip. So a cosecant and secant, they have a u going up, and then it asymptote, then it's u going down, asymptote, u going up. Okay. Now inverse works also. Now this thing right here will be helpful later on to some of these problems.
No.
Theorem. Continuity of exponential and logarithmic functions. An exponential function is continuous on its domain, all real. A logarithm function is continuous on its domain, all positive real numbers. Now, so this is exponential. Okay, it's raising to the exponent. The exponent is my variable. There's an exponent right there. So it is continuous, all real numbers. Okay, where a is going to be greater than 0 and a cannot equal 1 for this. So, what that is actually saying is, this is going to be just basically plugging in c here, all real numbers, c, and a has to be greater than 0. Okay, no negative numbers on that one. It's going to mess it up. Okay, so that's its domain, where a is going to be greater than 0, but for x is going to be all reals. The logarithm, okay, for this one right here, this is going to be any real number where c is greater than 0, okay, c is going to be greater than 0, so it's this number here. A has to also be greater than 0, that's your base, and a cannot equal 1. So for this one right here, my x could be any real numbers out of this, and then it's going to, we have restrictions on our a and c. All right, so let's actually put that into work without checking our phone every couple of seconds. All right, so determine exponential logarithm. Okay, right here. For this, a is a constant. Okay, just put it in there. So there is no variable. Okay, this one where you have x, you plug it in there. So Sine, okay, plug it in there. Cosine, just plug it in there. Okay, this one, my identities, these two right here are going to be very, very beneficial for you. Okay, this one right here, a to the x, a to c, these are what we just went over right there. And ta-da, I'm done. So that leaves us with a good 20 minutes. All right, don't forget, like and subscribe, right?